Hello everyone. I'm Shrey Sinha from the Department of Computer Science and Engineering at Indian Institute of Technology, Patna. I'll be discussing a presentation which will talk about survey of different loss functions used in image semantic segmentation. So first of all, let's learn why this is required. Like, what is the motivation behind semantic segmentation? So, for instance, just take a simple picture of a cat or a dog in it. To predict whether that the image is a cat or a dog, we can build a simple cat dog classifier. But what if there are more than one object in the image? We might be inclined to build a multi-label classifier, but we don't know the location of the either animal in the image. You can see in the right picture, like to predict, first of all, we have to identify what image is where. And this is where image segmentation comes in. Detection can build a simple bounding box corresponding to each class in the image, but it doesn't tell us anything about the shape of the object. Image segmentation works on every single pixel and classifies that pixel to a particular class. This helps in creating a pixel-wide mask for a more granular understanding of the object. Moreover, another thing that segmentation can be used in is when we have to separate or divides images into different parts for better processing. Like take an example of a picture of a house. There might be a lot of pixels that belong to a background. We don't need those pixels, right? We can simply discard them. And for this task, for just getting the house part, we can use semantic segmentation. Now, one extension of semantic segmentation that I would like to discuss is called instant segmentation. Semantic segmentation just describes the category of each object. Like you can see in the second picture below, we are able to identify tables from chairs. We are not identifying each instance of a chair. Like let's take a person or a picture of a roadway. We might be able to detect the person, the humans in there, but we're not able to detect this is person A, this is person B. Instant segmentation tackles that problem. Now, coming on to the loss functions used in segmentation, we have to keep in mind that generally segmentation problems are solved using deep learning algorithms and which use SGD or stochastic gradient descent approach to generally optimize and learn the objective. To learn an objective accurately and faster, we need to ensure that a mathematical representation of the objectives, which are known as loss functions, are able to cover even the edge cases. Now going on forward, one thing that we'll keep in mind is that whatever loss functions that we'll be discussing are for semantic segmentation instead of instant segmentation. Therefore, the number of classes at pixel level is restricted to two. Here, we'll be categorizing our loss functions into distribution-based, region-based, boundary-based, and compound loss functions. Distribution-based loss functions simply calculate the difference between the actual distribution and the predicted distribution and channel that into a loss function. Region-based loss functions try to maximize the region of true positives and minimize the ones that are false negative and false positives. Boundary-based loss functions are used on boundaries of prediction, and compound loss functions are simply a mixture of all of them. Uh, right here we have a table of the type and different classes of the loss functions. We can see that binary cross entropy, weighted cross entropy, balanced cross entropy, focal loss are all distribution based. Then we have region based loss functions, which are dice losses, sensitivity, specificity losses, diversity loss. Then we have boundary based losses, and then we have some compounded losses. The first loss that we shall be discussing is binary cross entropy. This basically measures the difference between two probability distributions for a given random variable or a set of events. Mathematically, this is defined at negative of y log y cap plus 1 minus y log 1 minus y cap. Here y cap is the predicted value by our prediction model and y is the actual label 0 or 1. Y, the actual label corresponds to actual distribution while our predicted label corresponds to our predicted distribution. This is why this is a distribution based loss. Uh, you can see a graph below which basically shows that at probability of 0.5, that is neither we are neither too sure that a that a pixel belongs to one class or other class, our loss is maximum, that is 1. Then we have one variant of BCE, which is called the weighted binary cross entropy. Here we aim to weigh down some positive examples. Like for instance, we might be inclined that the loss function captures more the actual image that we want to segment, like maybe a cat or maybe a house from the background. In such cases, when the data is skewed, like the background might be containing 90% of the pixels, we might be inclined to introduce a new variable called beta that basically we can alter to change the contribution of our classes. If we want to reduce the number of false negatives, we can simply set the beta value greater than 1 and decrease it to decrease the number of false negatives. Another variant is called a balanced cross entropy, which introduces a number for a hyperparameter for both the positive classes and the negative classes. Then we have focal loss. Focal loss proposes to weigh down easy examples, for which is for example the background pixels, which might be very easily classifiable. This is because the background pixels are generally much greater in number than the foreground ones that we are actually interested in. So we focus on the hard negatives using a modulating factor, which is 1 minus p t to the power gamma as shown below. Here p of t is basically the probability of the label. That is, this is equal to p if y is equal to 1 or 1 minus p if y is equal to 0 or otherwise. If we can notice that if we set gamma is equal to 1, this basically works like cross entropy loss function. Similarly, alpha ranges from 0 to 1 and it can be set as a inverse of class frequency or as a hyperparameter. Setting this as inverse of class frequency helps us because if we do so, then the pixels, the class that has a much more number of pixels in it, like maybe the background, can have less contribution to the loss as they're easily quantifiable or classifiable. Now, when an example is misclassified and pt is small, the modulating factor 1 minus pt to the power gamma is near 1 and the loss remains unaffected. Similarly, if pt tends to 1, that is the that is we are talking about the easily classifiable pixels, the factor goes down to 0 and the loss for well classified examples is downweighted. This is how focal loss works. And then we have the gamma value, the focusing parameter, which can adjust the rate at which easy examples are downweighted. Now we come on to dice loss. This is our first region-based loss that aims to minimize the mismatch or maximize the overlap regions between ground truth and predictive segmentation. The motivation behind this is consider an area of pixels that are being classified as a certain object. Let's say it's a positive class. And there might be one section that is actually the false positive, other section that are false negative, and one section that is actually the true positive section, which we actually want that is rightly classified. Now, what we want to do here is increase the true positive section and decrease the false negative and false positive section. So, this is known as dice coefficient. Dice loss is basically 1 minus dice coefficient. And in dice coefficient, the numerator corresponds to true positive and the denominator corresponds to false negative and false positive. This is fine for a discrete valued probability. But if we are talking about a continuous distribution, we formulate this as follows. 1 minus twice of y into p hat plus 1 divided by y plus p hat plus 1. Here the numerator corresponds to true positive and the denominator corresponds to twice the true positive plus fn plus fp. You might notice that we have added 1 in the numerator and denominator here to ensure that the function works in our edge cases where y or is equal to p cap is 0. Now we come on to Tversky loss. Tversky loss is based on the Tversky index, similar to how dice loss and dice coefficient are related. What we do in Tversky index is instead of just taking the true positive, false negative, and false positive simply in the denominator, we add a weighing coefficient beta to the false negative and the false positive. For instance, you can see that the PP cap section on the numerator corresponds to true positive, and the PP cap in the denominator also corresponds to the true positive. Then the second and third factors down in the denominator corresponds to the false positive and the false negatives. The Tversky loss can then be defined as 1 minus Tversky index. Tversky loss. Now we have one variant of Tversky loss called a focal Tversky loss, which focuses on hard examples by downweighing easy common ones. This basically uses the same idea of a parameter gamma that is basically a modulating factor. Now here we compare the different loss functions on the basis of our evaluation metrics that are dice coefficient, sensitivity, and specificity. For testing them, we have used a simple 2D unit model architecture of segmentation with 10 convolution encoded layers and 8 decoded convolutional transpose layers. We have used the NBFS skull stripping dataset, which consists of 125 skull city scans, and each scan consists of 120 slices. Our training batch size was 32 with Adam optimizer and the learning rate 0.001, and the data was split into 60 to 20 to 20 ratio. We can see that a focal Tversky loss performs well on dice coefficient, with the log cost dice loss performing the best on it. It also performs good on the sensitivity, and on specificity, the focal loss is the best. And now we have compiled a general use cases of a loss function. For instance, binary cross entropy works best when the distribution is equally in terms of the positive and negative examples, because in that we are not taking care of any skewed data or introducing a parameter for tuning the contribution of any classes. Then the weighted cross entropy is generally used in skewed data set. The balanced one can also be used in a skewed data set. Then similarly, the dice loss is used when we want to make it more tractable, and so on. So that is all from my side. Now our presentation will be taken forward by my teammate Ashutosh. He'll be discussing the different loss functions that are used in the general image classification technique. Thank you.
Hello, my name is Ashutosh Kumar and my roll number is 2101AI07, and I will be presenting on the topic improved loss function for image classification. So let's start with introduction. First of all, what is loss function? Loss functions measures the difference between the output data and the predicted data, and our goal is of course to minimize the loss value. One of the most fundamental loss function in image classification is softmax loss function, and it is often used in combination with some other loss functions such as cross entropy loss for accurate categorization. Softmax loss is adequate for simple image classification only, where the task is to categorize image into easily distinguishable classes, for example classifying animals into broad categories like dogs, cats, birds, etc. But when we talk about fine image classification, where the goal is not just to assign images to broad categories, but also to make subtle distinction within those categories, then softmax function is far from adequate, and we need some new loss functions. Here is the formula of the softmax function, and this output is basically between 0 to 1. Here in the numerator we have the output of a class in exponential form, and in the denominator we have the summation of all the outputs. So the the softmax function, the class which has the highest value of the softmax function is considered to be the class of the given image or data set. So the new loss function that we are going to discuss decreases the weight of easily classified samples from the perspective of probability. The training difficulty is lower in this new loss function, which was not in the softmax loss function. So now, how will we proceed? So we'll proceed in the following three ways. First of all, we'll propose our new loss function. Then we'll employ the new version to successfully lower the training difficulty. And finally, we'll apply the new version to deliver better classification performance compared to traditional loss functions. So this is the design of our new loss function, and in this formula, fx is defined as follows, where the value of fx is p when the value of y is 1, and in other cases the value of fx is 1 minus p. Now let's have a look at how loss function performs for different values of beta and gamma. We'll see the epoch and NMI graphs for different values of beta and gamma, and from the figure from the following figures which we'll be going to discuss, we'll see that when the value of beta is 4 and the value of gamma is 5 simultaneously, then the loss function performs the best. So this is the figure which is a graph of f1 and epoch, and we can see that the curve where the value of beta is 4 is performing the best with respect to the curve with other beta values. Similarly, in the case of NMI as well, the curve having the beta value 4, which is this black curve, is performing the best with respect to other beta values. And now we'll change the value of gamma. So we can see here that by changing the value of gamma, we can see here that when the gamma is 5, the loss function performs the best, both in the F1 and in the NMI graph. As we saw earlier, the formula of the softmax function. So this is the formula of the softmax function that we discussed earlier, and the new loss function that we have discussed can also be represented in terms of softmax as follows. So we are representing this new loss function in terms of softmax because we have been using softmax for classification from a long time, and expressing the loss function in terms of softmax kind of eases the task of classification. Here is the gradient of our new improved loss function, and here the softmax function is represented by s of x. Now we have discussed our loss function, what is its formula, its gradient, and how it performs for different value of parameters. Now we'll perform some experiments and see if our loss function performs better than other loss functions. So first of all, we'll determine the parameters. Basically, we have already determined the parameter, that is beta and gamma, that the value of beta should be 4 and gamma should be 5 simultaneously for our loss function to perform the best. Secondly, we'll compare our new loss function with other different kinds of loss function on the CIFAR-10 dataset. Then we'll verify how our loss function boasted good performance in various network architectures. Finally, we'll see performance of our loss function on other datasets. So first of all, we'll see the performance of our loss function on CIFAR-10 dataset, and then after that, finally, we'll see if our loss function is performing well on other dataset as well. So let's see the comparison of our loss function with other loss functions. So we'll compare multiple loss function on the CIFAR-10 dataset, which had 6,000 colorful images of size 32 cross 32, which are classified into 10 categories, each with 6,000 images. We'll divide this 6,000 images into two categories. One is training and other is testing. We have 50,000 images constituted of 5 training groups for training, and 10,000 images consisting of uh, 10 categories, which means that each category has approximately 1,000 images for testing. Now we will be conducting this uh, experiment on the GoogleNet architecture, and we'll be using 70 epochs, and we'll set the learning rate value to 0.0001, and we'll use a weight decay value of 0.004 and the momentum number of atom to 0.9. Now uh, after all this initialization of variables, we see that these are the two graphs which are the comparison of the various loss function on f1 and nmi parameters, and we can clearly see that in both the cases the new loss function, which is represented by the black line, is performing better than other loss function. The other loss functions such as triplet and margin loss are not as good as our new loss function. Now we saw that in GoogleNet architecture, our loss function was better than the traditional loss function. But but is it network data dependent, or is it performing better on other network architectures as well? So we'll now see the comparison of different loss function on ResNet, uh, on ResNet network architecture, and we'll see if our loss function is performing better than other loss functions such as triplet loss, margin loss, or not. So this is the graph of different loss function on the ResNet network architecture, and we can see that our new loss function is still performing better than other loss function. We can see from the figure that the two curves representing the NMI value and the F1 value of our new function are above the curves of other loss function. Despite slightly smaller NMI value of our loss than the triplet, the F1 value of ours is 0.06 higher than the F1 value of other traditional loss functions. Therefore, viewing, viewing comprehensively from the two standards of F1 and NMI together, we can say that our loss contributes greater than the triplet loss and margin loss. Accomplishment on other dataset. We saw that on CIFAR 10 dataset, our loss function was performing much better than the other loss functions. But now we'll compare our loss function and the traditional loss function on other dataset such as CIFAR 100 and Fashion MNIST. This is the graph which represents the performance of the various loss functions on the CIFAR 100 and the Fashion MNIST dataset. And here we can see clearly that our new loss functions curve, which is represented by black for NMI and uh, a dotted black for F1. And we can see that our new loss function is performing better than other traditional loss functions in these new data sets as well. So finally, moving on to conclusion. In this section, we proposed a new loss function for reducing the difficulty of training, and we saw that during our extensive experiments, our new loss function outperformed the effect of margin loss or triplet loss for both small scale and large scale datasets. Thank you.